The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So if you remember last time, we looked at parametric equations as a way of describing the motion of a point that moves in the plane or in space as a function of time or your favorite parameter that will tell you how far the motion has progressed. And I think we did in detail the example of the cycloid, which is the curve traced by a point on a wheel that's rolling on a flat surface. So we had this example where we have this wheel that's rolling on the x-axis, and we have this point on the wheel, and as it moves around, it traces a trajectory that looked more or less like this. OK, so I'm trying a new color. Is this visible from the back? Good. So no more blue. OK. So remember, in general, we are trying to find the position, so x of t, y of t, maybe z of t if we're in space, of a moving point along a trajectory. And one way to think about this is in terms of the position vector. So the position vector is just the vector whose components are the coordinates of the point. Okay, so if you prefer, that's the same thing as the vector from the origin to the moving point. So maybe our point is here, P. So this vector here is vector OP, and that's also the position vector R of t. So just to give you, again, that example, if I take the cycloid for a wheel of radius 1, and let's say that we are going at unit speed, so that the angle that we used as a parameter last time is the same thing as time. Okay, so then the position vector, in this case, we found to be, just to make sure that I have it right, t minus sine t and cosine t. No, 1 minus cosine t. Okay, same. That's a formula that you should have in your notes from last time, except we had theta instead of t because we were using the angle. But now I'm saying we're moving at unit speed, so time and angle are the same thing. Okay. So, OK. So now what's interesting about this is we can analyze the motion in more detail. Okay, so now that we know the position of a point as a function of time, we can try to study how it varies, and in particular things like the speed and the acceleration. Okay, so let's start with speed. Well, so in fact we can do better than speed. Let's not start with speed. So speed is a number. It tells you how fast you're going, along your trajectory. I mean, if you're driving in a car, then, It tells you how fast you're going. But unless you have one of these fancy cars with a GPS, it doesn't tell you in which direction you're going. And that's useful information, too, if you're trying to figure out what your trajectory is. So in fact, there's two aspects to it. One is how fast you're going, and the other is in what direction you're going. That means, actually, we should use a vector, maybe, to think about this. And so that's called the velocity vector. And the way we can get it, so it's called usually v. So v here stands for velocity more than for vector. And you just get it by taking the derivative of the position vector with respect to time. OK, now it's our first time writing this kind of thing with a vector. So the basic rule is you can take the derivative of a vector quantity just by taking the derivatives of each component. Okay, so that's just dx dt, dy dt, and if you have a z component, dz dt. Sorry, let me. Okay. So okay, so let's see what it is for the cycloid. So in the example of a cycloid, well, so what do we get when we take the derivative of this formula up there? Well, so t, the derivative of t is 1 minus cosine t. The derivative of 1 is 0. The derivative of minus cosine t is sine t. Very good. Okay. That's at least one thing you should remember from single variable calculus. Hopefully you remember even more than that. Okay, so that's the velocity vector. It tells us at any time how fast we are going and in what direction. So, for example, observe, remember last time at the end of class, we were trying to figure out what exactly happens near the bottom point, when we have this motion that seems to stop and go backwards. And we answered that one way, but let's try to understand it in terms of velocity. Well, if I plug t equals 0 in here, then 1 minus cosine t is 0, sine t is 0, the velocity is 0. So at that time, at that particular time, our point is actually not moving. Of course, it's been moving just before and it starts moving just afterwards. It's just, the instant, at that particular instant, the speed is 0. So that's a slightly maybe counterintuitive thing, that something is moving and at that time it's actually stopped. Now, let's see. So that's a vector and it's useful. But if you want just the usual speed as a number, then what will you do? Well, you will just take exactly the magnitude of this vector. So speed, which is a scalar quantity, is going to be just the magnitude of a vector v. Okay? So in this case, well, it would be square root of 1 minus cosine t squared plus sine square t. And if you expand that, well, so you will get, let me take a bit more space, that's going to be square root of 1 minus 2 cosine t plus cosine square t plus sine square t. Seems to simplify a little bit because we have cosine square plus sine square, that's 1. Okay, so it's going to be square root of 2 minus 2 cosine t. So at this point, if I was going to ask you when is the speed the smallest or the largest, you could answer based on that. See, at t equals 0, well, that turns out to be 0. The point is not moving. At t equals pi, that ends up being square root of 2 plus 2, which is 4. So that's 2. And that's when you're actually at the top of the arch. And that's when the point is moving the fastest. In fact, there it's moving twice as fast as the wheel, because the wheel is moving to the right at unit speed, and the point is also rotating, so it's moving to the right at unit speed relative to the center, so that the two effects add up and give you a speed of 2. Anyway, that's a formula we can get. Okay? Now, what about acceleration? So here I should warn you that there's a serious discrepancy between the usual, maybe intuitive notion of acceleration, the one that you are aware of when you drive a car, and the one that we'll be using. So you might think acceleration is just the derivative of speed. You know, if my car goes 55 miles an hour on the highway, then it's going at constant speed. It's not accelerating. But let's say that I'm taking a really tight turn. Then I'm going to feel something. You know, there's some force being exerted. And in fact, there is a sideways acceleration at that point, even though the speed is not changing. So the definition we'll take of acceleration is as a vector. And the acceleration vector is just the derivative of a velocity vector. So even if the speed is constant, that means even if the length of the velocity vector stays the same, the velocity vector can still rotate. And as it rotates, that produces acceleration. Okay? And so this is the notion of acceleration that's relevant in physics. For example, when you write F equals ma, that's really what a, you know, that's the a that you have in mind here. It's a vector. Of course, if you're moving in a straight line, then the two notions are the same. I mean, acceleration is also going to be along the line and is going to have to do with the derivative of speed. But in general, that's not quite the same. So, for example, let's look at the cycloid. If we take the example of the cycloid, well, what's the derivative of 1 minus cosine t? It's sine t. And what's the derivative of sine t? Cosine t. Okay. So the acceleration vector is sine t cosine t. So in particular, let's look at what happens at time t equals 0 when the point is not moving. Well, the acceleration vector there will be 0, 1. So what that means is that if I look at my trajectory at this point, well, then the acceleration vector is pointing in that direction. It's the unit vector in the vertical direction. So my point is not moving at that particular time, but it's accelerating up. So that means actually that as it comes down, first it's slowing down, then it stops here, and then it reverses, going back up. Okay, so that's another way to understand what we were saying last time, that the trajectory at that point has a vertical tangency, because that's the direction in which the motion is going to occur just before and just after time 0. Okay, any questions about that? No. Okay, so I should insist maybe on one thing, which is that so we can differentiate vectors just component by component. Okay, and we can differentiate vector expressions according to certain rules that we'll see in a moment. One thing that we cannot do, it's not true that the length of dr dt, so which is the speed, is equal to d length r dt. Okay, this is completely false, and they're really not the same. Okay, so if you have to differentiate the length of a vector, then basically you're in trouble. If you really, really want to do it, well, the length of a vector is the square root of the sums of the squares of the components, and from that you can use formula for the derivative of the square root and the chain rule and various other things, and you can get there. But it will not be a very nice expression. There's no simple formula for this kind of thing. Fortunately, we almost never have to compute this kind of thing, because after all, it's not a very relevant quantity. What's more relevant might be this one. This is actually the speed. This one, I don't know what it means in general. Okay? So let's continue our exploration. So the next concept that I want to define is that of arc length. So arc length is just the distance that you have traveled along the curve. Okay? So if you're in a car, you know, it has this mileage counter that tells you how far you've gone, how much fuel you've used if it's a fancy car. And what it does is it integrates the speed over time to give you the arc length along the trajectory of the car. So the usual notation that we'll have is S for arc length. I am not quite sure how you get an S out of this, but it's the usual notation. Okay, so S is the distance traveled along the trajectory. And for that to make sense, of course, we need to fix a reference point. Maybe on the cycloid, we'd say it's the distance starting from the origin. Or in general, maybe you'll say you start at time equals, t equals 0. But it's a convention. You could decide, if you knew in advance, you could have actually your car's mileage counter to count backwards, from the point where the car will die and stop working. I mean, that would be slightly freaky, but you could have certainly a negative arc length that gets closer and closer to 0 and gets to 0 at the end of the trajectory, or anything you want. I mean, arc length could be positive or negative. Typically, it's negative when you're before the reference point and positive afterwards. So now, how does it relate to the things we've seen there? Well, so in particular, how do you relate arc length and time? Well, so there's a simple relation, which is that the rate of change of arc length versus time, well, that's going to be the speed at which you're moving. Okay? Because the speed, as a scalar quantity, tells you how much distance you're covering per unit time. Okay? And in fact, to be completely honest, I should put an absolute value here, because there's examples of curves, maybe where your motion is going back and forth along the same curve, and then you don't want to keep counting arc length all the time. Actually, maybe you want to say that the arc length increases then decreases along the curve. Okay, I mean, you get to choose how you count it. But in this case, if you are moving back and forth, it would make more sense to have the arc length first increase, then decrease, increase again, and so on. So if you want to know really what the arc length is, then basically the only way to do it is to integrate speed versus time. So if you wanted to know how long an arch of cycloid is, you have this nice looking curve, how long is it? Well, you'd have to basically integrate this quantity from t equals 0 to 2 pi. And to say the truth, I don't really know how to integrate that. So we don't actually have a formula for the length at this point. However, we'll see one later using a cool trick and multivariable calculus. So for now, we'll just leave a formula like that, and we don't know how long it is. Well, you can put that into your calculator and get a numerical value, but that's the best I can offer. Now, another useful notion is the unit tangent vector. To the trajectory. So the usual notation is t hat. It has a hat because it's a unit vector, and t because it's tangent. Now, how do we get this unit tangent vector? So maybe I should have pointed out before that if you're moving along some trajectory, so you're going in that direction, then when you're at this point, the velocity vector is going to be tangent to the trajectory. It tells you the direction of motion in particular. So if you want a unit vector that goes in the same direction, all you have to do is just rescale it so that its length becomes 1. So it's v divided by magnitude of v. Okay. So it seems like now we have a lot of different things that should be related in some way. So let's see what we can say. Well, we can say that dr by dt, so that's the velocity vector, that's the same thing as if I use the chain rule, dr ds times ds dt. Okay? So let's think about these things. So this guy here, we've just seen that's the same as the speed. Okay? So this one here should be v divided by its length. So that means this actually should be the unit tangent vector. Okay, so let me rewrite that. It's t ds dt. So maybe if I actually state it directly that way, see, I'm just saying the velocity vector has a length and a direction. The length is the speed. The direction is tangent to the trajectory. So the speed is ds dt, and the tangent vector is t hat. And that's how we get this. Okay. So let's try just to see why dr ds should be t. Well, let's think of dr ds. Dr ds means, position vector r means you have the origin, which is somewhere out there, and the vector r is here. So dr ds means we move by a small amount delta s along the trajectory, by a certain distance delta s. And we look at how the position vector changes. Well, we'll have a small change. Let me call that vector delta r, corresponding to the size, corresponding to the length delta s. And now delta r should be essentially roughly equal well, its direction will be tangent to the trajectory. If I take a small enough interval, then the motion will be almost tangent to the trajectory, times the length of it will be delta s, the distance that I have traveled. Okay, maybe I should re-explain that on a separate board. Okay, so let's say that we have an amount of time delta t. So let's zoom into that curve. Okay, so we have r at time t. We have r at time t plus delta t. This vector here I will call delta r. The length of this vector is delta s. And the direction is essentially that of a tangent vector. Okay. So delta s over delta t, that's the amount, that's the distance traveled divided by the time. That's going to be close to the speed. And delta r is approximately t times delta s. So now if I divide both sides by delta t, I get this. And if I take the limit as delta t tends to 0, then I get the same formula with the derivatives and with an equality instead of an approximation. The approximation becomes better and better if I go to smaller intervals. Okay, are there any questions about this? Yes?
So the direction, it was the tangent to the curve, right? You said like when you draw your two vectors at tan equals t and then t plus delta t, the resulting vector was tangent?
Yes, that's correct. So, okay, so let's be more careful, actually. So you're asking about whether the delta r is actually strictly tangent to the curve, is that?
First time we're on the other side of that bottom curve, and your second time is somewhere else, it wouldn't be tangent to much of anything.
That's correct. Actually, delta r is not strictly tangent to anything. So maybe I should draw another picture. If I'm going from here to here, then delta r is going to be this arc inside the curve, while the tangent vector will be going in this direction. Okay? So they're not strictly parallel to each other, and that's why it's only approximately equal. Similarly, this distance, the length of delta r is not exactly the length along the curve. It's actually a bit shorter. But if you imagine a smaller and smaller portion of the curve, then this effect of the curve being a curve and not a straight line becomes more and more negligible. If you zoom into the curve sufficiently, then it looks more and more like a straight line, and then what I said becomes true in the limit. Okay? Any other questions? No? Okay. So, what happens next? Okay, so let me show you a nice example of why we might want to use vectors to study parametric curves. Because after all, a lot of what's here you can just do in coordinates, and we don't really need vectors. Well, actually, vectors being a language, you never strictly need it, but it's useful to have a notion of vectors. So I want to tell you a bit about Kepler's second law of celestial mechanics. So that goes back to 1609. So that's not exactly recent news, okay? But Still, I think it's a very interesting example of why you might want to use vector methods to analyze motions. So what happened back then is Kepler was trying to observe the motion of planets in the sky and trying to come up with general explanations of how they move. Before him, people were saying, well, they kind of move in a circle, but maybe it's more complicated than that. We need to add smaller circular motions on top of each other and so on. They had more and more complicated theories. And then Kepler came with these laws that said basically that planets move in an ellipse around the sun and that they move in a very specific way along that ellipse. So there's actually 3 laws, but let me just tell you about the second one that has a very nice vector interpretation. So what Kepler's second law says is that the motion of planets is, first of all, they move in a plane. And second, the area swept out by the line from the sun to the planet is swept at constant time. Sorry, is swept at a constant rate. From the sun to the planet, area is swept out by the line at a constant rate. Okay. So that's an interesting law because it tells you, once you know what the orbit of a planet looks like, it tells you how fast it's going to move on that orbit. Okay, so let me explain again. So this law says, maybe the sun, let's put the sun here at the origin, and let's have a planet. Well, the planet orbits around the sun, in some trajectory. So this is supposed to be light blue. Can you see it as different from white? No. OK, me neither. OK, it doesn't really matter. So the planet moves on its orbit. And if you wait for a certain time, then a bit later it will be here, then here, and so on, then you can look at the amount of area inside this triangular wedge. And the claim is that the amount of area in here is proportional to the time elapsed. So in particular, if the planet is closer to the sun, then it has to go faster. And if it's further away from the sun, then it has to go slower, so that the area remains proportional to time. So it's a very sophisticated prediction. And I think the way he came to it was really just by using a lot of observations and trying to measure what things were, what was true, what wasn't true. But let's try to see how we can understand that in terms of what we know today about mechanics. So, in fact, what happens is that Newton was quite a bit later. I mean, that was the late 17th century instead of beginning of the 17th century. So he was able to explain this using his laws for gravitational attraction. And you'll see that if we reformulate Kepler's law in terms of vectors, then, and if we work a bit with these vectors, we're going to end up with something that's actually completely obvious to us now. At the time, it was very far from obvious, but to us now, it's completely obvious. So let's try to see what does Kepler's law say in terms of vectors. Okay, so let's think of what kinds of vectors we might want to have in here. Well, it might be good to think of maybe the position vector and maybe its variation. So if we wait a certain amount of time, we'll have a vector delta r, which is the change in position vector over a certain interval of time. Okay. So let's start with the first step. What's the most complicated thing in here? It's this area swept out by the line. How do we express that area in terms of vectors? Well, I've almost given the answer by drawing this picture, right? If I take a sufficiently small amount of time, this grayed region looks like a triangle. So we have to find the area of a triangle. Well, we know how to do that now. So the area is approximately equal to 1/2 of the area of a parallelogram that I could form from these vectors. And the area of a parallelogram is given by the magnitude of a cross product. Okay, so I should say this is the area swept in time delta t. And you should think of delta t as relatively small. I mean, at the scale of a planet, that might still be, a few days, but small compared to the overall trajectory. So now let's remember that the amount by which we moved, delta r, is approximately equal to v times delta t. Okay? I'm just using the definition of a velocity vector. So let's use that. Well, sorry, so it's again approximately equal to r cross v magnitude times delta t. I can take out the delta t, which is a scalar. So now what does it mean to say that area is swept at a constant rate? It means this thing is proportional to delta t. So that means, so the law says, in fact, that the length of this cross product r cross v equals constant. Okay. R cross v has constant length. Okay. Any questions about that? No? Yes? Yes, let me try to explain that again. So what I'm claiming is that the length of the cross product r cross v measures the rate at which area is swept by the position vector. I should say with a factor of 2. 1/2 of this length is the rate at which area is swept. How do we see that? Well, let's take a small time interval delta t. In time delta t, our planet moves by v delta t. Okay? So if it moves by v delta t, it means that this triangle up there has two sides. One is the position vector r, the other one is v delta t. So its area is given by 1/2 of the magnitude of a cross product. That's the formula we've seen for the area of a triangle in space. So the area is 1/2 of the cross product r and v delta t, magnitude of a cross product. So to say that the rate at which area is swept is constant means that these two are proportional. Area divided by delta t is constant over time, and so this is constant. Okay. Now, what about the other half of the law? Well, it says that the motion is in a plane, and so we have a plane in which the motion takes place, and it contains also the sun, and it contains the trajectory. So let's think about that plane. Well, I claim that the position vector is in the plane. Okay, that's what we are saying. But there's another vector that I know is in the plane. Well, you could say, okay, the position vector at another time or at any time. But in fact, what's also true is that the velocity vector is in the plane. Okay, if I'm moving in the plane, then position and velocity are in there. So the plane of motion contains R and V. So what's the direction of the cross product R cross V? Well, it's the direction that's perpendicular to this plane. So it's normal to the plane of motion. And that means now that actually we've put the two statements in there into a single form, because we are saying R cross V has constant length and constant direction. In fact, in general, maybe I should say something about this. So if you just look at the position vector and the velocity vector for any motion at any given time, then together they determine some plane. And that's the plane that contains the origin, the point, and the velocity vector. If you want, it's the plane in which the motion seems to be going at the given time. Now, of course, if your motion is not in a plane, then that plane will change. It's somehow the instant, the plane in which the motion is taking place at the given time. And to say that the motion actually stays in that plane forever means that this guy will not change direction. Okay, so so Kepler's second law is actually equivalent to saying that R cross V equals constant, equals a constant vector. Okay? That's what the law says. So in terms of derivatives, it means d by dt of R cross V is the zero vector. Okay? Now, so there's an interesting thing to know, which is that we can use the usual product rule for derivatives with vector expressions, with dot products or cross products. There's only one catch, which is that when we differentiate a cross product, we have to be careful that the guy on the left stays on the left, the guy on the right stays on the right. Okay, so if you know uv prime equals u prime v plus uv prime, then you're safe. If you know it as u prime v plus v prime u, then you're not safe. Okay, so that's the only thing to watch for. So product rule is okay for taking the derivative of a dot product. There you don't actually even need to be very careful about the order of things, or derivative of a cross product. There you just need to be a little bit more careful. Okay, so now that we know that, we can write this as dr dt cross v plus r cross dv dt. Okay? Well, let's reformulate things slightly. So dr dt already has a name, in fact. That's v. Okay? That's what we call the velocity vector. So this is v cross v plus r cross what is dv dt? That's the acceleration, a, equals 0. Okay, so now what's the next step? Well, we know what v cross v is, because remember, a vector cross itself is always 0. Okay, so this is the same as r cross a equals 0, and that's the same as saying that the cross product of two vectors is 0 exactly when the parallelogram that they form has no area. And the way in which that happens is if they are actually parallel to each other. So that means the acceleration is parallel to the position. Okay? So in fact, what Kepler's second law says is that the acceleration is parallel to the position vector. And since we know that acceleration is caused by a force, that's equivalent to the fact that the gravitational force is parallel to the position vector. That means, well, if you have the sun here at the origin, and if you have your planet, well, the gravitational force caused by the sun should go along this line. In fact, the law doesn't even say whether it's going towards the sun or away from the sun. Well, what we know now is that, of course, the attraction is towards the sun. But Kepler's law would also be true, actually, if things were going away. So in particular, say, electric force also has this property of being towards the central charge. So actually, if you look at motion of charged particles in an electric field caused by a point charged particle, it also satisfies Kepler's law, satisfies the same law. Okay, that's the end for today. Thanks.